Picture this, the early 1930s when the universe was believed to be composed of just positively charged atomic nuclei, the electrons orbiting them, and the photon. But wait, there were anomalies, things that didn't quite align with our understanding. Then came the discovery of the neutron in 1932, which explains some of these anomalies. Yet, there were still questions left unanswered. Pauli, in 1930, hypothesized the existence of the neutrino to explain certain types of radioactive decay that didn't conserve energy and momentum. And yes, it took another 26 years for the neutrino to be discovered. The Dirac equation also predicted the existence of antimatter counterparts for particles like the electron, which were later discovered as positrons. But then, physicists were thrown a curveball with the discovery of the muon. An unstable particle with the same charge as the electron but hundreds of times its mass. This discovery turned physics upside down. And the story of the muon, it all began in 1912 with physicist Victor Hess taking a particle detector on a hot air balloon flight into the stratosphere. He hypothesized that high-energy radiation from space, known as cosmic rays, caused an electroscope to discharge over time, even in a vacuum. With a detection chamber and a magnetic field, Hess detected charged cosmic particles in abundance, including the muon. This discovery marked the dawn of cosmic ray astrophysics. Scientists then worked tirelessly to detect muons in terrestrial laboratories, and indeed, muons were found to make up 90% of all cosmic ray particles reaching Earth's surface. The muon's discovery was significant as it pointed to the existence of more particles and multiple generations of particles. It was the first clue that particles came in multiple generations. And that's just the beginning. The muon also demonstrated the effects of Einstein's theory of relativity. But what is the most intriguing part of all this? You'll find out soon enough. What's up, my amazing and curious folks? Ready to unravel mysteries together? I'm your host, Caesar, and joining me is the brilliant and insightful Sonia. Are you ready, Sonia?
Absolutely, Caesar. Hi everyone, can't wait to dive into today's topic.
Great! And before we get started, folks, don't forget to subscribe to the Curiosity Wonderland and hit that bell icon so you never miss an episode. Let's get into it! So, are we all following? This is where it gets really intriguing. This discovery that led physicists to turn their gazes skyward, to the cosmic rays bombarding our planet, all started with an electroscope. Picture this, an electroscope is just two thin pieces of conducting, metal foil, connected to a conductor and sealed inside an airless vacuum. When charged by a rod at the top, the like charges on the gold leaves repel each other, causing the leaves to spread out. What was absolutely mind-bending was that these electroscopes, even when placed in a vacuum, would discharge over time. Now you might be wondering, how could that be possible? Well, there's one word for it: cosmic rays. This discovery was made by none other than Victor Hess, an adventurous physicist and an avid hot air balloon enthusiast, who, in the year of 1912, had the brilliant idea to take a particle detector with him on a hot air balloon ride high into the stratosphere. And this is where our story really begins, with the first steps towards the discovery of the muon, this enigmatic particle that would soon revolutionize our understanding of the universe. Stay with us, because you won't believe what comes next. So, no matter how perfect the vacuum was around the electroscope, it still discharged over time. That's what was so mysterious. Even lead shielding around the vacuum apparatus didn't stop the discharge. And here's the interesting bit: the higher the altitude that the experiment was performed at, the faster the electroscope would discharge.
Hold on a second. So, are you saying that the discharge had something to do with altitude?
Exactly. The rate of discharge was faster at higher altitudes. This was what triggered Hess's big idea. He hypothesized that high-energy radiation, which has high penetrating power and originates from outer space, was the cause. He imagined this incredible zoo of particles zooming through space, and the higher he went, closer to the edge of Earth's atmosphere, the more likely he'd be able to observe these particles directly.
That's fascinating. But how did he actually detect these particles?
Great question. Hess devised a detection chamber that contained a magnetic field. So, any charged particles passing through it would curve and deflect. By analyzing the direction and curvature of these tracks, he could determine the particle's velocity as it moved through the detector, as well as its charge-to-mass ratio. It's kind of like watching a car make a sharp turn on a racetrack. If you knew the direction it was headed before the turn and saw how sharply it turned, you could estimate how fast it was going and get an idea of its weight. These early efforts were a smash hit. Hess started discovering particles in great abundance, effectively kickstarting the science of cosmic ray astrophysics. The first muon ever detected was found to have the same charge as an electron but was hundreds of times heavier due to its speed and radius of curvature.
This is truly mind-blowing. What a pioneering discovery.
Absolutely. And remember, we're just scratching the surface of this fascinating story. Stay tuned for more on the surprising muon. The discovery of the intermediate mass particle, the muon, was a big surprise in 1933. Its detection changed the face of particle physics. Many protons and electrons were seen in these early cosmic rays, and the first antimatter particles were discovered this way as well. But this new particle was a game changer. The muon had the same charge as an electron, but it was heavier than an electron and lighter than an antiproton. It was like a particle of an intermediate class suddenly revealing its existence. As we ventured higher in altitude, the number of detected cosmic rays increased. The majority were neutrons, electrons, and protons, while only a small fraction were muons. However, as detectors improved in sensitivity, they began detecting these rays even at lower altitudes, almost at sea level.
You know, this reminds me of my childhood. I was always fascinated by the night sky, constantly wondering about those distant stars and galaxies. My father, who was an amateur astronomer, nurtured this curiosity in me. On clear nights, we'd set up a makeshift observatory in our backyard, and he would teach me about constellations and nebulae. But what intrigued me most were his stories about cosmic rays, particles from outer space, invisibly bombarding our planet. I remember one night, he told me about these rays and how they were continually interacting with our atmosphere. He explained how these cosmic rays were like invisible rain, constantly showering down on us. It was both fascinating and a tad scary, like a science fiction tale come to life.
That sounds like an incredible childhood memory. And today, we know that what your father told you was absolutely right. When cosmic rays, these fast-moving particles from space, hit the upper atmosphere, they trigger what we call cosmic ray showers. The cosmic particles strike the stationary atmospheric particles, producing many new particles and antiparticles. The most common product of these showers is a charged, short-lived, unstable particle known as a pion. But among these particles, the one that caught everyone's attention was the muon. And we're going to delve deeper into its fascinating story. So stay with us. So, the charged pions that are produced from these cosmic ray showers decay incredibly quickly. Negatively charged pions decay into muons, while positively charged pions decay into antimuons, along with other decay products. These muons and antimuons are also short-lived but hang around much longer than the pions. On average, they have a lifetime of 2.2 microseconds, making them the longest-lived unstable particles, with the notable exception of neutrons which live for about 15 minutes. These muons, in our detectors, appear just like electrons, except they carry 206 times the mass of electrons.
So, the muons were discovered, characterized, and their behaviors explored quite swiftly, right?
Absolutely. By 1936, both the negatively and positively charged muons, indicating muons and antimuons, were distinctly identified from cosmic rays, just as with electrons and anti-electrons or positrons. In fact, in that same year, Anderson and Victor Hess were awarded the Nobel Prize in Physics for their pioneering work. In the following year, the discovery of muons and antimuons was independently confirmed in a cloud chamber. Here's a fun fact: at sea level, 90% of all cosmic ray particles reaching Earth's surface are muons, with neutrons and electrons making up most of the rest.
That's fascinating. So, muons aren't just real, but quite common, huh?
Exactly. To give you a sense of how common they are, if you were to hold out your hand with your palm facing up towards the sky, an average of 1 muon or antimuon would pass through your hand every second. Here's something to ponder, my audience. Can you imagine, right now, as you listen to our podcast, there are muons passing through your hand? How mind-blowing is that? This invisible shower of particles is happening all around us, all the time. It's like a hidden dimension of our world that we're just beginning to explore. Are your minds as blown as ours? And while we're on this journey of exploration, don't forget to like and share this episode of Curiosity Wonderland if you're enjoying the content. We're loving sharing these discoveries with you, and we hope you're loving learning about them. The particles and antiparticles of the Standard Model are not just haphazardly thrown together. They exist as a consequence of the laws of physics. And while we often depict quarks, antiquarks, and gluons in terms of colors and anticolors, remember that's just an analogy. The real science is even more captivating. When the physicist I. Irabi, who was notable for his Nobel Prize-winning discovery of nuclear magnetic resonance, heard about the muon, his reaction was, "Who ordered that?" At a time when so few particles were known, the addition of this strange cousin of the electron seemed like an inexplicable phenomenon. This heavy, unstable, short-lived particle did not seem necessary to explain the matter of our commonly experienced universe. But the muon was our first hint that more particles were waiting to be discovered. It also suggested that particles came in multiple generations. The first generation of particles consists of stable ones, up and down quarks, the electron neutrino, and their antimatter counterparts. The second generation has charm and strange quarks, muons, and muon neutrinos. The third generation consists of top and bottom quarks with tau and tau neutrino particles, along with their antimatter versions. The muon didn't just foreshadow these new discoveries, but it also gave us an exciting demonstration of Einstein's theory of relativity. For instance, the muons created from cosmic ray collisions originate at an altitude of about 100 kilometers. Considering the muon's average lifetime of 2.2 microseconds and its speed close to the speed of light, you'd expect it to travel only about 660 meters before decaying. However, at high enough energies and velocities, relativity becomes important. This allows many more muons to survive than would without the effects of time dilation. As a result, about 25% of the muons created in the upper atmosphere reach the Earth. Without relativity, that number would be something like 1 in 10 to the power of 20. That's a long shot, isn't it? Now, let's dig deeper into these fascinating phenomena and what they mean for our understanding of the universe. Are you ready? Let's dive in. Despite their short lifespan, muons manage to journey from their point of creation, which is more than 100 kilometers above, to Earth's surface without decaying. Seems impossible, right? But that's where the magic of relativity steps in. You see, relativity introduces this concept of time dilation. It means that particles moving close to the speed of light, like our muons, experience time passing more slowly than they do for us observers at rest. Without time dilation, we would never have discovered these cosmic muons. And how's this for a fun fact? Einstein, unknowingly, played a crucial role in helping us discover this fundamentally new form of matter. As we look to the future, understanding and manipulating these muons could lead to advances in experimental particle physics that no other type of collider can match. When you build a particle accelerator, the energy of your collisions is determined by three factors: the size of your ring, the strength of your magnetic fields, and the charge-to-mass ratio of your particle. Now, protons are typically used in accelerators like the Large Hadron Collider at CERN because of their high mass. But there's a catch. Protons are composite particles, meaning only a tiny fraction of their total energy ends up in the single quark or gluon that participates in the high-energy collision that we study. That's where muons come into play. They are elementary, fundamental particles, not composite ones. Plus, because of their much higher mass, they aren't limited by synchrotron radiation like electrons are. If we can master muon accelerators, meaning if we can create and confine muons and accelerate them to sufficiently high energies before they decay, we might be on the verge of unlocking the next frontier in experimental particle physics. Imagine the possibilities. We're standing on the precipice of scientific discovery, and I, for one, can't wait to see what's next. Now, isn't that a journey worth taking? Let's keep exploring this fascinating universe of ours, one curiosity at a time. Today, our understanding of the muon has evolved significantly from the days of hot air balloons and primitive detectors. These particles continue to provide a wealth of scientific discoveries. From illustrating the impact of time dilation on a particle's observed lifetime, to the possibility of leading to a new, superior type of particle accelerator, the muon has proven to be a key player in our quest to understand the universe. In fact, the experiment to measure the muon's magnetic dipole moment could be the key that ushers us into understanding physics beyond the Standard Model. It could reveal the potential existence of a fifth fundamental force of nature. That's how significant this seemingly ordinary particle could be. When the muon announced its existence unexpectedly in the 1930s, it was truly a surprise. Until then, no one had imagined that nature would make multiple copies of the fundamental particles that formed the basis of our reality. And yet, here we are, studying these particles that all decay, with the muon being the first, the lightest, and the longest-lived of them all. When we think of the muon, we should remember it as the first generation 2 particle ever discovered. It was our very first clue from nature about the true nature of the Standard Model. The muon, in its subtlety, has provided us with some of the most profound insights into the universe. Who'd have thought? It's fascinating, isn't it? And that, my friends, is the wonder of scientific discovery. We delve into the unknown, guided by curiosity and a drive to understand, and along the way, we uncover truths about the universe and our place within it. Now, let's continue this journey of discovery together, one step at a time. We've taken a deep dive into the world of the muon, a particle that turned the world of physics on its head in the 1930s. From hot air balloon experiments to particle accelerators, the muon has played a starring role in our continued exploration of the universe. It has revealed the existence of multiple generations of particles, demonstrated the mind-bending effects of relativity, and potentially opened the door to the next frontier in particle physics. In the grand scheme of things, the muon reminds us that in the quest for understanding the universe, size doesn't always matter, and the small can indeed be mighty.
Absolutely, it's been a fascinating exploration into the world of subatomic particles. Thanks for joining us today on this scientific adventure. If you enjoyed this episode, don't forget to blast that like button, share your thoughts in the comments, and spread the knowledge by sharing this episode with your friends.
As we say goodbye, remember, the universe is full of wonders waiting to be discovered, and we're here to uncover them together, one curiosity at a time.
Until our next journey, stay curious and keep exploring. Goodbye, everyone.
Goodbye. This fascinating journey into the world of the muon was inspired by an article titled How the Surprising Muon Revolutionized Particle Physics, written by Ethan Siegel and published on Big Think on October 12, 2023. You can find the full URL in the video description if you're curious to read more. And with that, it's time for me to sign off. Until next time, stay curious.